Now, our course is manufacturing processes 2 and the module 2 is continuing, which is mechanics of machining, and the lecture number 2.8. In the previous lectures you have heard that different aspects of cutting temperature that develop in machining, and this cutting temperature is very detrimental for the tool as well as for the job, and this has to be controlled or reduced. So, our topic today is control of cutting temperature, which is normally done by cutting fluid, and so our topic also includes that control of cutting temperature and cutting fluid application. Now, what are the course content within this lecture? Specific instructional objectives, the possible ways of controlling cutting temperature. There are different methods, only 3 methods are very common, we shall discuss. Then the purposes of application of cutting fluid, what do we apply the cutting fluid in the machining? To serve the purpose, what properties the cutting fluid should possess next, and next the principle of cutting fluid action, how does it work, the type of cutting fluid and how to select this cutting fluid for different purposes, different tool work materials, then demonstrate the methods of application of cutting fluids, because the effectiveness of application of cutting fluid depends upon how do we apply the cutting fluid. Now, what are the basic methods of controlling cutting temperature? There are 3 basic methods, all right. One is the proper selection of the cutting tools, the material and geometry, both of which play important role on the cutting temperature, magnitude and its effects. Next is proper selection of the process parameters. The principal process parameter is cutting velocity and next to feed. So, properly they have to be selected, keeping in view that metal removal rate remains unchanged. And third, but the most important, is proper selection and method of application of cutting fluid. Now, first the cutting tool, role of cutting tool material on cutting temperature and its effects. The cutting tool material plays important roles, quite significant role on the cutting temperature, because if the cutting tool is not very hard and wear resistant, then it will undergo plastic deformation and wear. So, there will be more heat due to friction, rubbing and cutting force. So, the tool has to be very hard and wear resistant and very stable, and the friction should be as less as possible. Some examples are given here. Say thin film coatings on the tools, say carbide. In the carbide tool, so this is the tool on which the chip flows. Here is the surface where rubbing takes place. Now, if there be a coating given here on the surface, then the chip will flow above this. Now, this coating that is given not only imparts wear resistance and heat resistance, but also this layer of coating provides anti-friction, reduces the friction, and if the friction is reduced, the cutting force will come down, cutting energy required will come down, heat developed will come down as temperature will come down. So, now the coatings, maybe this coating that is given on the tool can be hard coating or thin coating by chemical vapor deposition called CVD, or physical vapor deposition PVD, and there are various methods of giving this hard coating of material like titanium carbide, titanium nitride, alumina and so on, carbides and many materials. And sometimes the soft coating can also be given, say molybdenum disulfide. This is a soft coating. This, when pasted on the tool surface, this acts very well as lubricant, solid lubricant, which helps reducing force and hence heat generation and temperatures. Another example, say use of CBN tools. You know that CBN tool material is very hard and chemically stable against work material and temperature. Because of so hardness and wear resistance, the CBN tools remain very sharp all along, all right, and because of the sharpness and its retention, the cutting force does not increase, the cutting force remains low, and so cutting energy required also remains stable and the heat does not rise much. So, by using this kind of CBN tool, which is very expensive no doubt, but helps by reducing the cutting temperature. Third is thermally conductive ceramic tools. Now, ceramic tools are used widely nowadays for machining various materials like steels at high speed. Ceramic tools are non-conductive. So, the heat what is developed and received by the tool that remains confined at the surface. As a result, the heat, the temperature at the cutting point becomes very high and the tool gets damaged. Now, by increasing the thermal conductivity of this ceramic tool, heat is allowed to disperse throughout the matrix of the tool. So, the cutting temperature comes down into the cutting tool. How it is done? So, in alumina like ceramic, some metal like titanium carbide, hafnium carbide, tantalum carbide are added, they call charmat, and sometimes silicon carbide whiskers or rod, fine rods are added into that, which not only imparts toughness and strength, but also some certain amount of thermal conductivity that improves the performance of alumina tool. Another tool is Cylon. Next is metal ceramic composites. In ceramic like alumina or silicon nitride, some metal like iron, especially silver kind of thing is added, which not only increases the thermal conductivity, allowing dispersion of the heat through the matrix, but this silver functions when comes out at the top surface of the tool, that functions as solid lubricant and hence reduces friction, cutting force, energy and temperature. Now, the role of cutting tool geometry. Now, as you have heard number of times that along with the cutting tool material, the geometry of the cutting tool plays also very significant role on machinability of any material. Say for example, rake angle and clearance angle. Now, when we machine, say this is the tool and chip flows like this. This is the rake angle and this is the clearance angle. Okay. Now, why rake angle is given? You will please recall, rake angle is given to reduce the cutting force. If the rake angle is large and positive, the cutting force comes down. If the cutting force comes down, the mechanical energy required also becomes less and heat generation and temperature also come down. Similarly, alpha, this alpha also play. If alpha is not available, then there will be a lot of rubbing at the tool and the job, there will be a lot of heat generation, additional heat generation. If this clearance angle is too large, then the wedge angle becomes so small of the tool, then the temperature of this tool will be very high. So, this rake angle and clearance angle and some other angles have to be chosen very judiciously if we wish the temperature be reduced, but we have to keep something in mind. Control of cutting temperature by optimizing cutting velocity and just a minute. Now, here the rake angle and clearance angle play important role. Now, what about the compound rake tool and restricted contact cutting tool? You see that what is compound rake tool? The negative rake, positive rake and then built up edge, sorry, the chip breaker. So, when the chip will flow, it will flow like this and there is a positive rake and negative rake. This is called restricted cutting effect. What is the benefit? That the contact length becomes less. So, the frictional loss which is converted into heat will be reduced, and secondly the chip breaker will also control the friction, total friction, by controlling the chip tool contact length. So, by imparting this kind of tool geometry, the temperature can be controlled. Now, the principal cutting edge. What is principal cutting edge? This is the principal cutting edge. You remember that this is the cutting turning process, and this angle is principal cutting edge angle. Now, this principal cutting edge angle, if it is less, say like this much, then temperature will be less, and if it is large, then the temperature will be large. For example, it is like this. If you plot say phi of the cutting tool and temperature, it will go like this. So, this is a maximum when it is 90 degree. So, with the reduction in this principal cutting edge angle, the temperature can be reduced for same metal removal rate without changing velocity, feed, depth of cut. We can control the temperature to some extent by controlling the tool geometry. Similarly, the nose radius. The nose radius of the tool, if it is large nose radius, then the contact length between the job and the tool increases, and that helps reducing the average cutting temperature. So, this is how the temperature can be controlled by controlling the tool geometry. Next is control of cutting temperature by optimizing cutting velocity and feed combination. Cutting velocity and feed, these are the process, these are the process parameters, cutting velocity, feed and depth of cut, and product of these gives the metal removal rate or productivity. Now, productivity cannot be hampered. We cannot sacrifice, if we reduce velocity or feed, then definitely the temperature will come down, but we have to sacrifice the productivity. So, that has to be retained. Now, what we can do, keeping the product remaining same, T is not in our hand, it is not beyond control, but the velocity and feed can be controlled, either increased or decreased in such a way that the productivity will remain same, that is the value of the product will remain same, but the velocity can be reduced, can be increased, the velocity of feed can be reduced or increased, but whatever you do, keeping the product same. Now, while this variation will enable reducing the temperature, while doing so, while optimizing or varying or controlling the velocity and feed, something we have to keep in mind, the important things, which are number 1, that the cutting temperature is a function of this equation, velocity and feed. Now, here you see it is more susceptible to velocity because index is 0.5, and it is less susceptible to feed because the index is 0.25. This is one thing to be remembered. Second, increase in velocity. Now, if we increase the velocity, then what will happen? Suppose we increase the velocity, then the cutting temperature will increase. Why? Because the rubbing speed increases, more energy is input, so heat will increase and temperature will rise. But at the same time, with increase in velocity, the cutting force comes down. So, this is the cutting force. Now, when the cutting force comes down, the mechanical energy requirement comes down. So, this way the heat generated is reduced. So, here we find that increase in velocity has got two effects. One, it raises the temperature, it helps also to reduce the temperature, both way. So, we have to find out the total effect. Third, increase in feed. How does it affect? If we increase the feed, then force, say Pz, main force, that's according to equation it should go straight like this. So, as we increase feed, then the energy will increase and temperature will rise, but practically it goes asymptotic. So, we have to take into account this inclination or asymptoticness of the force with increase in feed. So, keeping all these factors in mind, we have to select velocity and feed in such a way that optimize the selection such a way that temperature becomes minimum, but keeping in view that MRR, the metal removal rate of productivity, does not change. We cannot sacrifice that. Next, we find the purposes of application of cutting fluid in machining and grinding. Now, what are the purposes? Very clear. The aim of application, improvement of overall machinability, ease of machining, reduce cutting forces and power consumption. So, that will help in saving energy as well as heat generation. Enhance tool life will improve product quality. So, in all the way we are getting benefited if the cutting fluid are applied, and but before application it has to be properly selected. But so we achieve all these benefits through application of cutting fluid through some processes. What are those? Through this cutting fluid application provides these benefits through cooling the tool and the job, then lubrication at the work tool and chip tool interface at the rake surface and the flank surfaces. So, at the rake surface and flank surfaces. So, the where rubbing takes place and heat is generated here and here. So, there has to be lubrication to reduce the force, friction force and heat generation. Then third purpose is cleaning the machining zone. In the machining zone, this is the machining zone where a lot of cheap particles and debris develop, and this debris or cheap particles if remain in position, they produce a lot of damages to the job as well as to the tool. So, these debris have to be removed immediately by washing away the particles by application of the fluid, and this is cleaning. And finally, protection of the nascent finished surface. When machining is done, when say machining is done, suppose this is a rod we machine and produce the finished surface. So, this is the finished surface. Okay. Now, this finished surface which is very nascent, and if it comes into contact with some gases like nitrogen oxide, sulfur dioxide, hydrogen sulfide which are present in the atmosphere or oxygen, this will be spoiled. So, there will be thin layer of cutting fluid stuck on the surface which will protect contamination of the surface from the gases, detrimental gases present in the atmosphere. So, this is how cutting fluid gives us the benefits. Now, to fulfill the purposes for which cutting fluid is applied, the cutting fluid should possess certain qualities, certain properties. What we say essential properties of cutting fluids to fulfill its purposes, but without sacrificing or damaging machine fixture tool work system. That is, it should not rust the machine tool parts, it should not mix with the lubricating oil and so on. So, what properties needed? Main properties, the main properties it need for cooling purpose, spreading and wetting. First of all, the cutting fluid should spread immediately over the tool surface and job surface, and it should wet the surface, otherwise it will not transfer the heat. Second, it should have high heat carrying capacity, that depends upon high specific heat, high thermal conductivity and high film coefficient of heat transfer. These three values if high, then the heat carrying capacity will increase, and you know water has got all these properties, and this is essential for the fluid. For lubrication purpose, what property we need? Again wetting and spreading property, it has to spread the cutting fluid. Then high lubricity, it should be oiliness has to be there, but without foaming and gumming, because if the cutting fluid undergoes foaming and gumming under the high pressure and temperature, then this will hamper the lubricating effect. So, this has to be prevented, that kind of fluid has to be selected. Next is chemical stability. This cutting fluid should not decompose or change under the temperature, and this should be also non-corrosive. It should not corrode the machine parts and tools and jobs. High flash and film boiling point, so that it remains stable up to a high temperature, and it should not be volatile, it should not evaporate out, it should not be volatile. Even if it is volatile, less volatile, and it should be the cutting fluid should be odorless, there should not be any smell, bad smell or any kind of smell, and preferably colorless, that is transparent. Why transparent? Because if it is transparent, then the visibility will be there, the worker, the operator of the machine can see what is going on exactly at the cutting point. So, it should be as far as possible transparent, but odorless is a must. Then non-toxic, this cutting fluid should not harm the operators like skin, or eyes, should not be harmful to the eyes or respiratory system and all these things should be non-toxic, and available and low cost. The cutting fluid you may select, but it should be available, otherwise how can you use it, and of low cost is obvious, it has to be available and economic. Now, what is the principle of cutting fluid action, how really it works? So, it has got 4 purposes: from bottom, protection of the surface, cleaning the surface, that is washing away, then lubricating and cooling. Now, how does it cool? The cooling it does, by the coolant, whatever you use, the cutting fluid, that has to reach in the rubbing zone. This is the rubbing zone, this is one rubbing zone and this is another rubbing zone, that is the chip tool interface and these flank surfaces. Now, here the cutting fluid has to reach to take away the heat from the sources. If it cannot, at least from the outside, this will heat, this is called bulk cooling. This will be able to cool the entire job and tool to remove the heat from the cutting zone to some extent. The lubrication, for lubrication, where lubrication is necessary, or for friction reduction, where friction takes place, where there is a rubbing. Where rubbing takes place? 2 places. One is the chip tool interface, where tremendous amount of rubbing takes place under high pressure and temperature, and at the work tool interfaces, that is flank surface. These are the areas where this cutting fluid should reach to cause lubrication or oiliness. But how does it work? This is the contact length, this is the chip tool contact length, this much, and this is called natural contact length. This chip tool contact length has got 2 parts. One part is plastic contact length, which is bulk contact or solid contact, and other one is elastic contact through high points of asperities. Now, the cutting fluid when applied, it can reach within this elastic contact zone, but it cannot reach in the plastic contact zone. All right. So, and again it has been found that with increase in velocity, when the cutting velocity is increased, the entire contact length becomes plastic, where cutting fluid cannot reach, and if it cannot reach, then it cannot lubricate. So, here you can see that with increase in cutting velocity, the ratio of plastic contact length to elastic contact length gradually increases and becomes 100% after at certain point at a very high speed, and the elastic contact zone totally disappears and the cutting fluid cannot enter at all, and lubricating effect disappears. So, it is stated that with increase in velocity, the lubricating effect gradually diminishes. So, at high speed, lubricating type of cutting fluid is not preferred, cooling type fluid has to be selected. Now, how does it work really at this zone? And this zone, this elastic contact zone, the cutting fluid is pulled by the capillary effect or the viscous drag or capillary effect or surface tension, and when this cutting fluid, which contains some chlorine, chloride, sulphide or phosphate, that reacts with the work material or the chip material at its bottom surface under high temperature and pressure, the reaction product, the physical reaction that takes place, produces another layer of material at the chip tool interface within this elastic region, which is very soft in nature, which is low shear strength and functions as solid lubricant. Therefore, within elastic region, the friction decreases drastically because of this formation of a low shear strength film by physical reaction between the fluid or the chlorides of the fluids and the work material. Sometimes these chlorides or phosphates or sulphide kind of additives are deliberately added in large quantity to enable reduction of this friction under heavy cut. These are called extreme pressure additives, which can be chloride, which can be phosphate, which can be sulphide. If the cutting temperature is low, say around 200 to 350 degree centigrade, like when you machine say mild steel by high speed steel, then chloride type of extreme pressure additive can be added to impart more lubricity or lubricating property. If the temperature is moderate, then phosphate is better, and at high temperature, say heavy cut or machining very hard and stronger steels, then sulphide type of extreme pressure additive is added into the cutting fluid to impart more friction resistance by lubrication. So, what next? The general types of cutting fluids. Now, we have seen what are the purposes of application of cutting fluid. Then we have seen what to serve the purposes, what properties the cutting fluid should possess, and then what are the different types of cutting fluids available and developed so far. We have to be familiar with them, and we should also know their characteristics, the characteristics of those fluids, and then we have to select very properly. What are the different types of cutting fluids normally used? Air blast. Air blast is used when cutting fluid in the liquid state cannot be allowed or causes problems, like only cooling, and air blast is given only for cooling and cleaning, not for lubrication. Then comes water. Water is having the maximum specific heat. It is the best cooling agent. So, best coolant, but its lubricating property is almost nil, and it also causes rusting to the machine parts. So, in that way water is not preferred, but for cooling purpose water is best, no doubt. Then what is soluble oil? Soluble oil, to impart some anti-rusting property, little oil is added into water, and this is called soluble oil. This is also called slurry. It looks like milk, in milk fat particles remain suspended, and for which it looks white. Here also oil, little amount of oil is added into water, and it is dispersed by atomization, and it looks like milk. So, this oil is generally used for imparting some lubricity and anti-rusting characteristics. Now, what is soluble oil then? Water basically 90 to 98% and 2 to 10% cutting compound. This is oil cutting compound. What is comprised of? Basically oil, some emulsifying agent like detergent, which breaks the oil into fine globules to remain suspended, and some extreme pressure additive like say chloride, phosphate or sulphide, if required, is also added for heavy cuts. Then cutting oils. The cutting oil is basically mineral oil in which some vegetable oil, animal oil, etc. are added. In addition to that, if required for heavy cuts, some extreme pressure additive is also added. This together is called cutting oil. Now, the chemical fluids often used. What is this? This is basically water based. Chemical fluids are water based, mainly water, and this is very suitable for some kind of material like aluminium, pure copper, which are soft, but aluminium and copper and their alloys are very sticky. Because of this stickiness, it is very difficult to machine. It causes a lot of friction and this built up edge formation and entangling. So, some fluids have to be used. These are called chemical fluids, where some organic or inorganic materials are dissolved in water. Why? Now, these chemical fluids are again two types, chemically inactive type or chemically active type. Chemically inactive type, which does not chemically act with the work material or tool material, and this is basically used for high cooling, where high speed machining of material, where high speed high temperature develops, which has to be cooled, then chemically inactive type chemical fluid is preferred. But if we want lubricating also along with cooling, then chemically active type, where the chemical fluid is preferred, and these fluids are suitable for aluminium and copper, and this moderate one for cutting copper at heavy cuts, because this gives moderate cooling effect and lubricating effect. Now, sometimes the solid lubricant is also used, solid or semi solid lubricants, neither liquid nor gas. These are liquid like paste or wax or soaps or graphites or say material like molybdenum sulphide are applied. How is it applied? Either directly on the work surface or impregnated or dispersed into the tool material, and these materials functions as lubricant, solid lubricant at the chip tool interface. At the chip tool interface, friction takes place, and if this molybdenum sulphide or solid lubricant in a very thin layer reaches or remains, then the friction will come down and the cutting force will come down. And sometime sorry, some special cutting fluids are also applied for extreme cooling, like say cryogenic fluid, that liquid nitrogen, liquid carbon dioxide, these are used. These are used mainly for cooling purpose, extreme cooling, because the temperature is very low, minus 196. And another important aspect of cryogenic cooling is that environment friendliness, because oil type cutting fluids creates problem, and it is very hazardous and creates pollution, where cryogenic fluid like liquid nitrogen and liquid carbon dioxide do not create this kind of problem. Sorry. Now, the selection of the cutting fluid. So, the special type I told, cryogenic fluid like liquid nitrogen and liquid carbon dioxide. Liquid nitrogen is cheaper, easily available and low cost, so it can be used. Now, the principle of cutting fluid action, which has been described. Next is selection of cutting fluid. How shall we select the cutting fluid? Because while selecting the cutting fluid, 2 points have to be kept in mind, that the cutting fluid is selected based on the work material, tool material and the machining condition, because the behavior of the cutting tools depend upon the work material, tool material and machining condition. All fluids are not suitable for all work material or all tool materials or all machining conditions. You will gradually see. Then cooling type. Basically, we need cooling and lubrication from the cutting fluid. So, the cooling type, cutting fluid is suitable for high speed machining of easily machinable materials like say steel, low carbon steel or low alloy steel by carbides or high speed steel. And we should take lubricating type for low speed machining of both easy and difficult to machine materials like say hard steels or strong steels or other materials. Why? At low speed the chip tool contact is elastic, where these at the aspirated joints the cutting fluid is dragged in, but at high speed machining the cutting fluid cannot enter at the chip tool interface. So, there is no chance of any lubrication, only cooling is possible. That is why it is rightly stated that cooling type should be chosen for high speed machining and lubricating type for low speed machining, especially when the work materials are very tough, hard and strong, and there is a chances of built up edge formation. Now, let us have some example. Cutting fluid used for common materials. Say grey cast iron is one of the most common and widely used engineering material. What shall we use? What kind of cutting fluid we should use for grey cast iron? Preferably dry, because if we take any cutting fluid in the liquid form, that mixes with the dusty particles or chips of the cast iron, and that forms a material like a paste, and this paste causes a problem. Not only that, it increases the friction and damage of the tool. So, this fluid should be avoided in machining grey cast iron, which produces very fine tiny discontinuous chips with graphites. But where cooling is very much required, suppose when you machine grey cast iron by say carbide or ceramic at high speed, lot of heat will be generated. That has to be removed. That can be done by air blast. It is dry, it is also dry, air blast for cooling and cleaning purpose, but no lubrication. But when we machine or grind even grey cast iron for finishing purpose, surface finish and surface integrity, then little amount of oil can be mixed with water, and that can be used carefully for finishing purpose. Otherwise, for machining grey cast iron, it has to be done either dry or with air blast. Now, for steels, what shall we do with the steels? Now, again steels are of different types, mild steel, plain carbon steel, alloy steel, within plain carbon steel, low carbon steel, medium carbon steel, high carbon steel, in alloy steel, low alloy steel, high alloy steel, and so on. And steels are machined by different materials also, maybe machined by high speed steel or say carbide or ceramic. Depending upon the kind of steel and kind of the tool used, the cutting fluid has to be selected. Not only that, whether it is low speed or high speed, that will also matter. So, all these three factors should be kept in mind while selecting the cutting fluid. For example, say if the mild steel, is machined by high speed steel. Now, you know high speed steel cannot withstand high temperature, it machines at low speed. Now, when machined by high speed steel at low speed, soluble oil, medium grade soluble oil has to be used. What is the ratio? 1:20:30. 1 is cutting compound or oil and 20 to 30% water, so 30 times. So, 1 part is cutting compound or oil and 20 to 30 parts water. So, it is very diluted, and this is used for soft steels, that is low carbon steel, low alloy steel, and we should use neat oil for stronger steels. Why? Because little bit oiliness or lubricating property is needed. So, oil is added or oil is used, but we have to use extreme pressure additive along with the oil while cutting under high pressure and temperature, that is large force, where there are lot of chances of friction and built up edge formation. So, this is a heavy cut, and extreme pressure additive will enhance the lubricity of the cutting fluid, and that will help machining say hard steels and high alloy steels and so on by high speed steel. But if machined by carbide, what is the feature of carbide? Carbide as such is brittle, number 1. Carbide can withstand very high temperature. These are the two. Generally, when machined by carbide, it machines at high speed, so high temperature will develop, but carbides are brittle. So, if there be any thermal shock in the tool or fluctuation in the cutting temperature, then the tool may break by thermal fracture. So, these things have to be kept in mind. Keeping that in view, we have to select thinner oil, thinner soluble oil, that is water and oil, thinner, that is 1:40 like that, for soft steels, low carbon steel, low alloy steel, because here oiliness is not required, what is needed mostly cooling purpose. Then thicker oil, that is 1 part and 10 to 20 parts water for stronger steels, which is machined at slightly lower speed and needs lubrication. Then straight sulfurized oil, no soluble oil, for more lubrication property and heavy and low speed cuts. Then if it is a heavy cut or high alloy steel, then extreme pressure additive has to be used along with the oil to get more lubrication. But as I told you at the beginning, occasionally the steels are cut by carbide under dry condition to prevent thermal shocks, if it is machined at high speed, especially soft steels at high speed. Now, these steels are also machined by ceramic tools. Ceramic tools are more brittle, so more care has to be taken, but ceramic tools are used at even higher speed. So, there is more heat generation and more temperature, and because of high speed, the high temperature will be high, and the entire contact length of chip and tool will be plastic contact length. So, there is no chance of entry of cutting fluid and lubricate at the chip to interface. So, better either you cool it by so soluble oil or light oil or dry, preferably dry. You can do it by dry or air blast, and for finishing purpose sometimes little oil can also be added. In that case, the ceramic tool has to be high performance ceramic with adequate strength and toughness, otherwise this will fracture into pieces because of this water based or soluble oil or water based oil. Next, let us see aluminum and its alloys. I told you already that machining of materials like aluminum, its alloys, and copper and its alloys are very difficult. Why? They are soft, no doubt, their shear strength is low, but they are very sticky, and they remain stuck with the tool surface and forms lot of built up edge, seizure, and all these things add very large amount of friction. So, because of that it becomes difficult, and this cutting tool also gets spoiled because of such high temperature and all this, because of the friction temperature also rises. So, what is done? Special care has to be taken, that aluminum and copper are very reactive. So, aluminum and copper have to be preferably machined dry, if feasible do it by dry condition, but you can also use light but oily soluble oil. Light, it should be light, that is the amount of oil should be very less, but that oil should be oily type, say not only mineral oil, little bit compound oil, and this has to be used. But we can use straight neat oil like kerosene for stringent cuts, that is more complicated cuts, or say form tools and other things, when you machine with form tools, cut threads or forms, then little bit straight neat oil is needed to lubricate the tool as well as the chip interface. Now, again the copper and alloys, copper and alloy and its alloys, water based fluid is best, all right, water based fluid, but water based fluid is called chemical fluid, all right, where now the as I told you, the chemical fluid are of two types, active type or inactive type. What kind? If it is a high speed machining, then generally we use inactive type, but if it is heavy cut, tougher grades, then neat oil and copper neat oil, or you see we can active type water based or chemical fluid can be used. So, chemical fluid inactive type should be used for machining copper and its alloys at high speed and where the force is not much less, and neat oil or this active type chemical fluid for tougher grade of copper alloys. Now, stainless steel is another important material and heat resistant alloys, like a nickel alloy or titanium alloy. These are very difficult to machine and create lot of friction and chances of built up edges which damage all these things. So, this has to be prevented. So, what is recommended? High performance soluble oil, that is thick oil with extreme pressure additive, or neat oil with high concentration of extreme pressure additive. High performance soluble oil is a good amount of oil in water, maybe 1:10 in that ratio, or neat oil with high concentration of extreme pressure additive. Now, this can be mixed with soluble oil also. So, this is necessary to enhance lubricity and prevent friction between the work material and the tool. Now, the effectiveness or the benefit of the cutting fluid application depends not only on how do you select depending upon the work material, tool material, cutting velocity or feed or nature of cut, heavy cut, free cut. It also depends how do you apply the cutting fluid. Okay. Now, when you say how, this type method of application of cutting fluid, when you say methods of application of cutting fluid, that is very important, that also governs the effectiveness of the cutting fluid action. Now, with these methods actually are understood in respect of flow rate. What are the different methods of cutting fluid application in respect of flow rates? It can be drop by drop, you apply the cutting fluid drop by drop just like a miser at the cutting point and from the top surface under gravity, or it can be applied as a flood, is a flood under gravity. So, the lot of a stream of cutting fluid will be flooding profusely the cutting zone and take away heat and the lubricate and the flood under gravity. Now, sometime we use in the form of jets, so that the cutting fluid is enabled to reach or go close to the chip tool interface or work tool interfaces by slightly lifting or shifting the chip. So, this makes the cutting fluid action very effective in the form of jet, but the consumption is high and here it is little expensive. Mist, that is mist with compressed air. So, with compressed air some liquid is mixed in atomized state. So, liquid is first, say oil is atomized and by compressed air and then projected at the cutting point, that economizes the use of cutting fluid, but it makes effective, and this is applicable for lubricating purpose, mainly for lubricating purpose, but the jet for cooling. Now, there is another method called jet method. This is basically centrifugal process through grinding wheel or pores. Now, this shows this jet method. Actually, this later jet comes from the abbreviation of the name of the inventor of the this method, a German method, where scientists have developed this method. So, this is called jet cooling. What is the principle? Principle is it is grinding, it is applied in grinding process. Suppose this is the job, this is the job, this is the job, then this is the surface of the job which has to be finished by grinding, and this is the job on the other view, this is the other view, side view, this is the workpiece, and this is the grinding wheel. Instead of applying grinding wheel, there is a cutting fluid in this way. Normally, conventionally we apply cutting fluid in this direction, in this place or from here, but in jet method, to make it more effective, what is done? It is cutting fluid is sent through the sent axially, and there is a bush which has got holes, radial holes, number of radial holes here, and through the holes the liquid goes inside the wheel. The wheel is porous, because of the pores, the pores are filled with oil, because when it rotates at high speed, the air entrapped into the pore are thrown out. So, vacuum is created, these evacuated spaces are filled with oil or cutting fluid, and then it goes out centrifugally at high speed tangentially, all right, when it is rotating in this direction, and a part of the cutting fluid reaches at the cutting zone or the grinding zone very effectively. Normally, cutting fluid which we apply only 3 to 4% is effective, remaining are really simply consolants, it does not reach the cutting zone. The remaining part of the cutting fluid that cools from outside by bulk cooling, but not reaching at the cutting zone. But if we do it the jet method, say more amount of cutting fluid will really reach at the cutting zone where temperature is maximum. So, this is more efficient, but this is very expensive, no doubt, but as and when required it can be attempted. Now, the method of application of cutting fluid again in respect of direction. Now, it can be applied from top of the surface. So, this is the machining going on by the cutting tool. So, you can apply the cutting fluid from the top or from the side or from both the sides or from front or from back or even from the bottom. So, the cutting fluid can be applied from different directions, and depending upon that the efficiency will be different. Of course, it depends upon what kind of machining is going on. For grinding, for turning, for milling, the way will be different. Now, this is the cutting. What are the methods? What are the common directions we follow? From top. So, this is the cutting tool and this is the workpiece, and we put from top cutting fluid here, okay, from top. Or suppose this is the cutting tool, this is the cutting tool and this is the chief flows. So, you can give it from top, from front, from bottom and from the sides. So, these are the various ways of applying cutting fluid as mentioned, from top, from front or back, from the side or both sides, and from bottom externally by flooding. And here is another method shown over here, from bottom through the tool, because of the main problem that is the main source of heat is the chip tool interface rubbing in this region, all right. So, the cutting fluid here does not reach if applied conventionally. So, what is done? A through hole is made through the cutting tool and cutting fluid is passed through this, pushed through this at under high pressure, and it reaches at the chip tool interface to some extent, and that makes lubricating and cooling more effective. That helps lubricating and cooling much better. So, this is how the cutting fluid has to be learned. What is the purpose of the cutting fluid application? What properties it should needed? It should possess, and then how it has to be selected that all these things have to be done very carefully, because if the selection of the cutting fluid is wrong, then instead of benefit it can create more problem. Okay. So, it has to be selected very carefully. Now, there are certain exercises given for the purpose. After going through this lesson that you have heard, now you can have some questions, and I have given you some say objective type of questions. So, there is a point given and there are 4 answers. The question is there and there are 4 possible answers, and one of them is correct. You have to identify the correct one. So, identify the correct answer from the given options. 4 options are given. For example, say cutting one, question number 1 or the point number 1, cutting fluid is employed in machining for cooling the tool and the job, that is 1. Second answer, lubricate at the rubbing surfaces and cleaning the machining zone, or all of the above, that is 3. Which one is correct? Definitely you know cutting, what is the purpose of cutting fluid? Cooling, lubricating, cleaning. So, all these are essential, that the answer is D. This is how answer has to be found out. What is the next one? Another one, for example, say for same tool work materials and speed, feed and depth of cut, the average cutting temperature will decrease. How? With increase in principal cutting edge angle. What is principal cutting edge angle? Just observe, this is the turning process. This angle is principal cutting edge angle. With increase in principal cutting edge angle, you remember that if the principal cutting edge angle and temperature, it goes like this. So, the temperature decreases with the decrease in the cutting temperature decreases when the principal cutting edge angle is decreased. With the decrease in principal cutting edge angle, this is the answer, and the auxiliary cutting edge angle has got no role. This angle phi 1 has got no role on temperature. This is more important, and when it is low, then the temperature will be low. So, this is correct answer. See another, the work material which is machined by high speed steel tool geometry, high speed steel tool generally in dry condition. The work material which is machined by high speed steel generally in dry condition is cast iron, one answer possible, mild steel, stainless steel and low alloy steel. Now, it is very clear that high speed steel is prone to solid solution, formation of built up edge, etc. Mild steel, stainless steel, these are continuous type of chip, they need lubricant and cutting cooling, but grey cast iron it should not. So, this is the answer. Extreme pressure additive is mixed with cutting fluid in improving the power of lubrication. What is that? Power of cooling. Extreme pressure is additive for what purpose? Is it for cooling? Is it for increasing lubrication property? Is it for cleaning, or it is for protection? You understand that this is for lubrication purpose, to increase lubrication purpose. Now, here you see the jet method of cooling is surface grinding. The cutting fluid is employed. Jet not in jet method of cooling is surface grinding is employed in the form of flood under gravity. In jet method, how the cutting fluid is employed? In the form of flood under gravity, or in the form of jet at the grinding zone, drop by drop, or none of the above. Really it is sent through the ports centrifugally of the wheel. So, none of these, therefore, this is the correct answer D. And last 7, in machining copper, I remember, which is very soft and sticky under heavy cut, one should use what kind of? Light soluble oil, active type chemical fluid, inactive type chemical fluid and compound oil. Now, definitely this chemical fluid will be used, that is water based fluid for copper and its alloys, and which one, active or inactive type? Since it is heavy cut, so active type is preferred. So, this is the answer. So, this you can see in the next page. So, these are the answers of the questions. What you can see, you can find out many more questions in many books here and there and try to solve those problems. So, this ends. Thank you. Now, today we are starting module 3 that deals with machinability connected with machining, and the topic of today's lecture will be concept of machinability and its improvement. Now, what are the specific instructions of objectives or the contents of today's lecture? After hearing this lecture, the students will be able to conceptualize what is machinability and state its definition and what are the criteria of judgment of machinability. Next, the students will be able to illustrate how machinability is governed by several factors: chemical and physical properties of the work material itself, the processing parameters like cutting speed or velocity, feed, depth of cut, etc., cutting tool, its material and geometry.